Consider a simple compressible control mass of fixed chemical composition. A simple compressible control mass of fixed chemical composition The Maxwell relation which can be written for such a system are four equations relating the properties P, V, T, and S. Let me write with the uppercase the Maxwell relations are four equations relating the properties P, V, T, and S. This will be found to be useful in the calculation of entropy in terms of the other measurable properties to be useful in the calculation of entropy in terms of the other measurable properties. Measurable properties. The Maxwell relations are most easily derived by the considering the different forms of the thermodynamic properties relation, which was the subject of the section 8.5. The two forms of this expression was previously expressed as du T ds minus P dV and dH T ds minus V plus V dP. Note that the mathematical representation, these expressions are the form U is a function of S and V, and H is a function of P and S. In mode of which entropy is used as one of the two independent properties, these questions, in these relations. This is an undesirable situation in the entropy is one of the properties that cannot be measured. We can, however, eliminate entropy as an independent property by introducing two new properties and thereby two new forms of the thermodynamic property relation. The first of these is the Helmholtz function A. Let me write the relation again. du T ds minus P dV and dH T ds plus V dP. U S B and H a function of S and P. S cannot be measured from so to eliminate to eliminate S, we have these relations. We introduce a function, the first of Helmholtz function, A equals to U minus TS and differentiating and substituting to the equations the U equals to T ds minus P dV, we can write d A, making an integration du T ds plus S dt du minus T ds minus S dt. So dA equals to, this is minus P dV S dt. So A is a function of V and T, which are not the form of the property relation utilizing T and V as an independent properties. T and V are independent The second property is the Gibbs function G. G equals to H minus TS or TH minus TS dg dH minus TDS minus SDT. In the properties we have dH equals to TDS plus VDP. So these properties dH minus TDS equals to VDP. dg TDS VDP SDT. A fourth form of property relation, this form using T and P as the independent properties. G is a function of T and P. So we can write again here volts Helmholtz relation or function. Gives relation d g equals to a fourth form of the property relation. This form using T and P as the independent properties. Since these equations are all relations involving only properties, we conclude that these are exact differential and therefore are the general form of the dz n dx plus n dy. In which equations relates the coefficient m and n with the s in the follows form. Equation 1410, which was du TDS minus PdV, can be written as this relation. Similarly, from the equation dH TDS plus VDP, we can write this relation for T round P on round V, round T on round V at S constant should be equals to round V on round V on round S. At P constant. You should note that the U is a function of the S and V. And from the relation dz and dx plus dy and m on z equals round z or round d. In this mathematical expression, on m on round phi at x constant should be equals to round n on round x at y constant. So applying to this relation, we can obtain this. We had also for a Helmholtz function which say that they are minus SDT PdV. In this case, M round S on round V at T constant equals to round P on, it is a function of T and V. So round P on round T at V constant. The next relation is for Gibbs function, Tg minus S dt plus V dp, a function of T and P. M is S, we can write this relation. Round S on round P at T constant equals to round V and round T at P constant. These four equations are known as the Maxwell relations. The Maxwell T on round V minus round P on round S round T on round P round V on round S at P. The next relation, round P on round T at V, round S on round V at T, and also round V the Maxwell relation for a simple compressible mass. And the great utility of this equation will be demonstrated in later section of this chapter. As was noted earlier, this relation will enable us to calculate entropy change in terms of the measurable properties, pressure, temperature, and specific volume. Measurable properties. A number of other useful relations can be derived from these equations and the previous equation, for example, for U. We have AU T ds minus P dV dH T ds plus V dP and dA T minus S dt P dV dG S dt plus V dP. Round U, from this relation we can calculate that round U on round S at V constant, these properties. Round U on round S at V constant equals to T, and round U on round T round V at S constant equals to minus P, and round H on round S at P equals to T, and round H on round P at S round G on round P round G on round P As already noted, the Maxwell relations just presented are written for a simple compressible substance. It is readily evident, however, that similar Maxwell relations can be written for substances involving other effects, such as surface or electrical effects also. For example, for the general case, du TdS PdV electrical pressure and electrical, this is tension, and du, for example, for TdS plus TA involving surface effect. We have this relation, rho T on rho A. It is a function of S and A, and S constant should be equals to the rho S and A constant. Other Maxwell relation could also be written for such a substance by writing the property relation in terms of different variables, and this approach could also be extended to systems having multiple effects. This matter also becomes more complex when we consider applying the property relation to a system of variable composition, a topic that will be taken up in section 49. The next section is thermodynamic relation involving enthalpy, internal energy, and entropy.